Pause the video, give us a go yourself first. Okay, I'm hoping you've given it a go yourself first. We need to turn this into Denary. Pretty simple. Step 1, I'm going to go to my Exponent straight away, and I'm going to see that it adds up to 5, and it's positive. Step 2, I'm going to look at the Mantissa, I'm going to see that there's no decimal points. That basically means it's going to be here. Step 3, I need to shift it to the right because it's positive, and 5 spaces, or places, sorry. 1, 2, 3, 4, 5. So that is where it's going to be now. So look, boom. I'm going to get rid of this one. Happy days. I've lost what step I'm on. I'm going to place all the values at the top. I don't need to go any further because there's nothing there. 8 plus 4 plus 1 is 13. So that is 13. That is the easy part. After the decimal point, we're then going to be doing, I'm going to do 0.5 and I'm going to do 0.25. We add those two together, gives us 0.75. Happy days. That is it. Step 2, or question 2, pause the video, give it a go. Okay, we can tell this is not normalized because, and I'm going to use geeky terms, the first, in fact, I've got this down here, so I'm going to write it here. The first 2 bits of Mantissa are the same. Then I'm going to give my example, 0, 0, not 0, 1. Easy. Happy days. So this question is telling us that we want to normalize the floating point number in 2's complement form. Well, the number is 13.75, so we don't need to do any conversions. In essence, we can just keep it as it is already because it's already in its 2's complement form. So the Mantissa is going to be exactly the same as what we've been working with already, where we've got, and I'm going to fill it out. My pen's gone. But actually, let me just count the number of bits. We've got 4 bits, and we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 4 bits and 4 bits. Fine. Now, I don't need to include this 0 here. It's irrelevant. It doesn't add anything to anything we're doing. So I'm actually going to start here when I'm filling it out. That's going to be our most significant bit. So I'm going to do 0, 1. And this is important because we want to normalize it. 1, 0, 1, 1, 1, and then at the end a 0. So what we've done is very simply got rid of a trailing 0 here. Now, the decimal point is originally going to be here. So I've kept the decimal point here, 13.75, 13.75 here. But what we want to do is normalize it. Just to clarify that it's in the right place, we've got 2 1s here, and we've got 2 1s here. Yes, we've got this new trailing 0, but that's, again, not going to add any value. So what I'm going to do is I'm going to shift the decimal point 1 place, 2 places, 3 places, 4 places. So that's where I want it to go now. And now we've got a normalized floating point number in 2's complement form. So the exponent will be 0, 1, 0, 0, 4. Okay, so this time we are going straight away into a positive normalized floating point number. So even if you're using 2's complement, it's still going to be the same because it's positive. What I'm going to do is I'm going to put in our number. So we're going to have to make 11 to start off with. If I just do, let's just count the bits. So 1 bit, 2 bits, 3 bits, 4 bits, 5, 6, 7, 8. So we've got a byte we're dealing with. So let's calculate 11 to begin with. I'm going to go 1, 2, 4, 8, 1, 0, 1, 1. We know that we're going to be dealing with normalized and normalized numbers, so I'm going to add another bit here to make it 0 so that we have a chance to put a decimal point there. So this makes 11. Point for now. We need the what's it called? The 6.25 aspect. So this is going to be 0.5, and we want that to be a 1. We then want 0.25, and that is going to be a 0. We're then going to have our 0.125, and that is going to be a 1. So if we add this up, we're going to have 11.625. Nice and easy. So that'd be my step 1, to put it into its just normal binary floating point representation without it being normalized. Then we need to normalize it. So the decimal point is here to make it 16.25, but we know the rule is going to be 0, 1. So I'm going to shift it 1, 2, 3, 4 spaces. There. So my exponent is going to be 4. Then we've got everything else which we're going to fill in, which obviously will be 0, 1, 0, 1, 1, 1. Yeah, I've got enough ones. 0, 1. And there we go. That makes plus 11.625. Pause the video, give this a go yourself for negative 11.625. So we're going to do the same sort of process. We're going to take the positive number first, which was 0, 1, 0, 1, 1, 1, 0, 1. We're then going to obviously do our flipping. 1, 0, 1, 0, 0, 0, 1, 0. We're then going to do our plus 1. I'm going to do that in a different colour. I like to just fill these up with zeros. Why? Because my brain can't visualize. It's a birth defect. 1 add 0 gives you 1. 1 add 0 gives you 1. 0, 0, 0, 1, 0, 1. So, if I was to put that in here right now, we've got a 1, we've got a 0, we've got a 1, we've got a 0, 0, 0, 1, 1. The exponent stays the same because we're just shifting it to here, so it's still going to be 0, 1, 0, 0. Simple as that. Why is the exponent the same? Because when we first put it into first normal form, which is this, the decimal point was here. When we turn it to 2's complement into the second normal form, and we flip the numbers, etc., the decimal point was still here. We needed to move it to the first 1, 0. To move it to the first 1, 0, we had to shift it 4 spaces, just like we did up here. The decimal point was in the same space, and we want to flip to there. You know the drill. Pause the video, give both of these questions a go yourself. Okay, so let's rock and roll. I'm going to first of all solve this bottom part. 1, 2, 4, 8, 16, 32, 32, and then let's put in place our point. So our exponent is 1, 2, 4. So that makes 5. So we're going to add it in this position here. So we start in the 0, 0, and we go 1, 2, 3, 4, 5. Don't ask me why I put placeholder values out first. I don't need to really. Oh, bomber. The decimal point was here. Okay, now we can do our placeholder values. 1, 2, 4, 8. 8 plus 2 is 10. 0.5. So 10.5 is our answer. So again, started off here. I went 5 to the right because it told me to in the exponent. I then put the placeholder values on. I did my little addition. Now what we're going to do. Okay, so step 1, we got the 7.5. So let's turn that into its binary counterpart. 1, 2, 4. So 1, 1, 1. That gives us a 7. 0.5 here. That gives us a 7.5. But remember, when we're doing normalized floating point, I'm going to add another placeholder value here and put a 0, so we've got our opportunity to normalize it. I'm then going to shift the decimal point 1, 2, 3 spaces. So the exponent's going to be 3. In terms of this, it's going to be simply 0, 1, 1, 1. So our decimal point is there when we normalize it. And 1. So we've got our 4 ones. And the rest are zeros. So we fill up the rest here. And there we go. That is 7.5. Okay, now what we're going to do is do negative 7.5. This is easy. We're going to take our 7.5 positive, so that's 0, 1, 1, 1, 1, 0, 0, 0, and we're going to flip it. So it's going to be 1, 0, 0, 0, 0, 1, 1, 1. Fill it up with zeros. Perform some binary addition. 1 out of 1 is 0, carry the 1. 1 out of 1 is 0, carry the 1. 1 out of 1 is 0, carry the 1. So 1, 0, 0, 0, 1. So that is now our Mantissa. 1, 0, 0, 0, 1, 0, 0, 0. Our exponent is still going to be in the same position. It's still going to be 3 because the decimal point hasn't changed when we did our conversion. So we just shift it again to the left. So it's going to be 0, 0, 0, 0, 0, 0, 1, 1. Okay, pause the video. Give this question a go yourself first. Alright, state the significance of this binary number. Well, this binary number is basically the largest positive normalized number based on bits available. Why? Well, if we can't put a 1 here, because now that we're dealing with a number which is not normalized. So that is a fact. If we were to put a 1 here and have a 0 here, you could say it's bigger, but no, this is representing a negative number. So this is the largest positive number we can have. With the exponent, if we were to put a 1 here, it shifts the decimal point to the right rather than to the left, which means that we're going to make the number smaller. So this is the largest Mantissa, an exponent we can possibly have for a normalized number based on the amount of bits. What would happen if a positive number is added to this number? Well, it's going to create an overflow. It becomes too large to represent for the amount of bits. Number versus bits available. Pause the video, give this a go yourself first. So we need to create the largest and the smallest normalized floating point number based upon the amount of bits we've got for the Mantissa and the exponent. So the largest exponent we can have would be 0, 1, 1, 1. That will be the largest based on this. In terms of our Mantissa, this would be the largest we can have. Makes perfect sense. So we've got our decimal point here based upon the exponent itself. In terms of the smallest positive number, not anything to do with negative, positive number, the smallest positive number would be 0, 1, because we need it to be normalized, and then everything else would be 0. And if we were to fill this out 1, 0, 0, 0, remember this will be -8, 4, 2, 1. We're using 2's complement. Keep that in mind. So this would be the smallest positive number that we could actually have as floating point. Some people make the mistake of saying this. Think about what that will do to the decimal point. This in itself is smaller. Okay, so this one's a little bit more tricky as a question. They're trying to catch you out. So pause the video, give this a go yourself first. Right, so we're dealing with 202. So let's convert that into binary. So 1, 2, 4, 8, 16, 32, 64, 1 to 8. So 1 bit, 2 bit, 3 bit, 4 bit, 5, 6, 7, 8. So we're dealing with a byte. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, we're dealing with 2 bytes here. One for the exponent, one for the Mantissa. So that'll be a 1, that'll be a 1, that'll be a 0, that'll be a 0, that'll be a 1, that'll be a 0. I believe, hold on, let's just add up. So 1 to 8 plus 8 is 136. 136 is 64 is 200. 202. Okay. We've got a problem. This would fit into here perfectly. Oops. It's a shame I can't copy out perfectly. 1, 1, 0, 0, 1, 0, 1, 0. It fits perfectly. Happy days. And we've got a decimal point here. So here. The problem is it wants it to be normalized. We know that this is not normalized. So we still have to do this like we've been doing for the previous questions. We add another placeholder and we put a 0 there. So look at the situation now. We put a 0, then we do our 1, our 1, our 0, our 0, our 1, our 0, our 1. But we're then missing this value. It would be here. There is not enough bits. But that is the situation we've got. We've been forced to put this into this Mantissa. We've been forced to. Then we want to normalize it. So decimal point, we need to shift it 1, 2, 3, 4, 5, 6, 7. 1 space, 2 space, 3, 4, 5, 6, 7. Well, let me just, I forgot we've deleted. So hold on. When we're doing our decimal point, we've got to take all of this into account, including the number which has been chopped off. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So that's where we want the decimal point to go. So the exponent will be 0, 0, 0, 0, 1, 2, 4, 8, yeah. 1, 0, 0, 0. That'll be our exponents. So that is our answer. Obviously there's an issue with that. It's not accurate. It's not accurate. We know that. Really, we've created it as an overflow. We'll talk about that another time. Point being, it's not accurate, but that's how you handle this situation. You've got your Mantissa size, you've got it to be normalized. If it wasn't normalized, we can put this whole number in there. We don't need this extra one. We can just leave it like that. But it is normalized. So it wants to do -202, so pause the video, give that a go. Okay, so what we're going to do is that we're going to flip our numbers. So we're going to flip what's inside here. So we're going to have, let me just add the 256. We're going to have let's move that there. So we're not going to include that when we put it down here. So now let's turn it into 2's complement. Sorry, let's flip it. 1 0 0 1 1 0 1 0. Now let's flood it with zeros. Now let's do our addition. 1 1 0 1 1 0 0 1. Okay. I'm going to put that into here. 1 0 0 1 1 0 1 1. And obviously the exponent's still going to be the same. 0 0 0 0 1 0 0 0. And hey presto, we're done. Pause the video, give these questions a go yourself first. Okay, so let's just count the number of bits. 1 2 3 4 5 6 7 8 9 10 bits, and exponent 1 2 3 4 5 6. Okay, we've got 513. 513 into binary. Let's do 1 2 4 8 16 32 64 128. We need to go to 256. So 256 is 9 bits. 512 is 10 bits. To make it to 513, we need that. There you go, 513. Great. But we want this to be normalized. Remember, when we do it normalized, we need this leading bit, most significant bit, to be a 0. Therefore, what is the issue? Mantissa has 10 bits. We need 11 bits to store 511 as normalized, otherwise overflow. That's the reality. So I could show you this in my answer. This wouldn't be in the question, it'll be further up. But I can actually show it working out in my answer to prove it needs to be an overflow. We've got 13 bits. Sorry, we've got 11 bits here. So, describe an alteration to the way the floating point numbers are stored to enable this number to be stored accurately. Easy. We need the number of bits for the Mantissa to increase to 11, but we need a trade-off. And then reduce exponents to 5 bits. There you go. Okay, so when we're dealing with negative Mantissas or negative exponents, don't forget in 2's complement this will be a negative number. So I'm going to do x for now. As would this be? This would be a negative number. So this will be negative 8, 4, 2, 1. To work out our exponent, it will be negative 8 plus 4 plus 2. If we did that, the answer would be negative 2. So what I'm going to do is I'm going to write out our Mantissa and show you how this impacts everything. Negative 2 is basically going to mean we're going to shift these binary numbers 2 places to the right. So if we've got our decimal point here, what's going to happen is this. This number is going to become here. So we're going to start with a 1 because we're shifting it 2 spaces to the right. Then we've got a 0, so I've just done these 2. Then it'll be a 1, 1, and then everything else will be a 0 after that. And I'm going to fill this in with a 0, and then I'm going to put a point in and a 0 here because we shifted it 2 places to the right. So we've got this one, which is now here, and we need 2 new zeros, one to be on the left side of the decimal point and one to be on the right. Let me get that. So that's now what we're dealing with. The second thing what we've got to do if we're dealing with a negative Mantissa is we've got to find the most significant one. Basically, the most significant bit which contains a 1, which is this one. Right here. If I was to put in our decimals here, so this would be 0.5, this would be 0.125, sorry, it wouldn't, that would be 0.25, my bad. This would be 0.25, this would be 0.125, this one, I'm just going to do it below, it's here, let's say it's going to be 0.0625, and this one is going to be 0.03125. Okay, so I said we're going to find our most significant one bit, which is containing a 1, and it's this. So what I'm going to do is I'm going to put a little negative here. Represent we're dealing with negative numbers. So our calculation is going to be negative 0.25 plus, so we've got nothing there, it's going to be this one here, plus 0.0625 plus 0.03125. By doing that, we get 0.15625, and that is our answer with a negative because it's a negative number, so it should be negative 0.15625. So again, we've taken this, we've taken a negative exponent, and we've got this as an answer. I will do some more negative questions post this little clip. If you want to carry on, not a problem. And okay, pause the video, give this one a go yourself first, dealing with a negative number. Okay, so let's sort this out. Step 1, let's do our exponent. 1, 2, so that gives us 3. So I'm going to go 1, 2, 3. So what we have now is 1, 0, 0, 1.11. If we just like narrow it down. This is obviously going to be 0.25, this is going to be 0.5. 1, 2, 4, 8. But this is negative 8. So if we're going to add this all together, we're going to have negative 8 plus 1, which gives us 7. But we've also got to take into account for plus 0.5, which equals 6.5, plus 2.5, which equals 6.25.